The next method we are going to present here, it's called the second order Runge-Kutta method, or it's also called the trapezoidal method. Again, this is a method to solve for first order ordinary differential equation. That's the equation, this is the usual initial condition. But actually, that's not a new method. Actually, this is the same as the previous midpoint method, but it's re-elaborated and redefined. We are redefining some of the parameters arising in this midpoint method. So we're presenting it in a different way, and I think it's in a more convenient way. So first of all, here that's the method the midpoint method that we actually already derived before. Here we are using another way for naming the time index, for example. Instead of using I, here we're using the J on one hand, and on the other hand, instead the time step, instead of calling it delta t, we're going to call it h. But otherwise, it's pretty much the same. So here, as you can see, that we are using that expression here, in order to evaluate the y function evaluated at time j plus 1, just using information on the two previous times. If you remember, it had some, the application of this method is quite straightforward, but the only problem is the initialization, so that when you are in the first step, when you are applying that for j equal to 0, we had to define the value for y at time minus 1. So that's the problem we had. So that's the midpoint method. And now in the Runge-Kutta method, we are going to use the same method, but we are going to make some little changes. And which are the changes that we're going to make? They are the following. So in the Runge-Kutta method here, we're going to double our time step, so that in this Runge-Kutta method, we do have that we are going to call delta t is going to be 2 times h. So that's going to be, in the Runge-Kutta method, our delta t, as it's written here. But if we are doing that, if we are doubling our time step, it means basically that this time in the middle disappears, and therefore we're going to use another index in order to define and specify the times, and we're going to use the index I. Therefore, that's going to be in our Runge-Kutta method the time ti, so tj minus 1 is going to be ti, and the tj plus 1 is going to be the ti plus 1. So, and the time step from one time to the other, it's delta t. So considering that differences, basically, we're going to express this midpoint method, but considering these redefinitions we have just mentioned. So again, that will be the following. So here, the time j plus 1 will be the time I plus 1. That's what we do have here. Here the time j minus 1 will be the time I. That's what we have here. Then 2 times h will be delta t here. Okay, then the f function is evaluated just in the middle time. So that's why this tj will be here just in the middle. That here the tj will be here, will be ti plus delta t over 2, the half of delta t. So this is the tj. And then, on the other hand, we have to consider also the y function evaluated at time tj, just in the middle. So it will be the wave function evaluated at time ti plus delta t over 2. And for that, we are going to use, besides that, we are going to use our the first order, the linear Taylor expansion around time ti. So this would be actually the y function evaluated at time ti plus delta t over 2, which is the time step we do have here, times the derivative of y with respect to time evaluated at time ti, which basically is the f function evaluated at time ti and yi. So just including everything as we have here, that would be the second order Runge-Kutta method that can be actually, and it's usually written in the following way. So for that here, we are going to define like two different functions. This the k2 will be all these, the one we do have here, which actually it's the same as we do have here. This is what will be the k2 function. And that's inside the k2 functions, we also have another k1. And the k1 will be delta t times the f function evaluated at time ti and yi, which actually it comes from the Taylor expansion we have considered here. Okay, so just considering the definition of these two different functions, the k2 and the k1, then we do have that the Runge-Kutta method is expressed in this way. So as we have seen here, we have derived the second order Runge-Kutta method, which actually is based on the midpoint method, as we made some redefinitions of the internal parameters of the 10 time steps that appeared in the midpoint method. And the advantage that we are getting with that is that this method, expressing it that way, it does not have the initialization problem that appeared in the midpoint method. We are eliminating that problem, which is a huge advantage, so that we can apply in a more straightforward way this method again, because all the rest, I mean, the order of the method is actually the same as the midpoint method. It is actually the same. This is an explicit method. So everything, all the rest is the same. The thing is that considering that as we don't have that initialization problem, we say that it's more straightforward to apply.